Hi everyone. Welcome to part 1 of a lecture covering mechanical properties of materials. In this part, we're going to briefly describe what a material property is and introduce some key concepts which are needed to appreciate some of these properties. Let's start with what a material property is. When we think about material properties, maybe we think about optical aspects. Is it translucent or opaque? Perhaps the ability to conduct electrical current or heat. These are electrical and thermal properties, respectively. One material property you're all familiar with is density. This is a physical material property, the relationship between volume and mass. Note that regardless of how much volume of a given material you may have, or the mass of that material, the density is a property that relates them. It is therefore a property independent of the amount of material. Here we can see that different classes of materials have differing densities. These densities are valid under particular conditions or a state, for example, under ambient conditions. When we describe mechanical properties, we need to apply the same approach. This is critical when selecting materials for a given application. Mechanical properties are also decided by a critical state that is achieved. For example, we do not directly compare loads or forces to compare materials, nor would it be particularly useful to singularly compare the amount of deformation imparted to different materials. Furthermore, comparing these properties under vastly different conditions would also not be appropriate, such as at elevated temperatures. In this lecture, we're going to cover some important mechanical material properties and develop some terminology and techniques to capture them. In this part of the lecture, we'll cover Poisson's ratio, and we'll also cover Young's modulus, also referred to interchangeably with the elastic modulus. With what is developed here, you'll be able to look at how the elastic modulus can be directly acquired from a standard testing approach, the uniaxial tensile test. In part 2, we'll go further with describing more mechanical material properties using the approaches covered in this part. Consider a cylinder of material being loaded uniaxially. By uniaxially, there is only one force acting on it along the central axis, in the z direction. The specimen will change shape over the period from zero load to some load F. It will lengthen along the z-axis and dilate equally along the x and y axes due to symmetry. The length will change from L0 to LF, while the diameter and therefore cross-sectional areas will decrease due to dilation. We can consider this event both from a loading perspective, whereby a state of stress is developed, as well as how much deformation is imposed by this state of stress, a quantity called strain. Starting first from a stress perspective, stress is defined as the force or load over an area at a given point in time. As force F increases, the instantaneous area will decrease from A0 to AF, describing a state of increasing stress. As a matter of convenience, engineers often use the term engineering stress, where the change in the area is not captured, instead using the starting cross-section at the beginning of the loading event. As a matter of further convenience, engineering strain is often employed as well. Turning our attention now over to deformation, the strain in the z direction is captured on an engineering basis by the starting length and the final length. However, if one wishes to capture the true strain, or how strain is actually evolving, then one must use a formulation that uses a rate. Here we can see that this rate of change in strain in the z direction can be reformulated such that the true strain is a function of engineering strain. You may note the different nomenclature, S for engineering stress and lowercase e for engineering strain. Sigma and epsilon are usually used to describe true quantities. It is emphasized that throughout this course, engineering quantities of stresses and strains will be employed, regardless of whether they are S's or sigmas, E's or epsilons. So we have the ability now to describe strain along a singular direction. If we were to write out the expressions for strain in the other cardinal directions, we would end up with the following for z, x, and y. As it turns out, there's another very useful material property which describes the ratio in which a component will deform in one direction versus others, if one were to assume that the material behaved the same in all different directions, as most metallic materials do. This latter description, behaved the same in all different directions, is an indication of isotropy. For small strains and asserting isotropy, there is a relationship between the transverse and longitudinal strain called Poisson's ratio, represented by the Greek letter nu, which looks like the English character V. Here with engineering stress approximately the same as true stress, nu can be applied to solve for strains in all different directions. Note the negative sign for the strain in the x direction. This is due to convention. While the strain in the z direction increases due to a greater length in the z direction, the strain in the x and y directions is negative, as these dimensions are getting smaller from the condition where there was zero load. Plotting the evolution of stress with strain under the conditions required to apply Poisson's ratio, one arrives at a figure on the right, whereby the stress is a linear function of strain. Up to this point, we've only considered small strains. It's now important to provide boundaries to the behavior that was discussed previously. If one were to keep increasing stress from 0 through to sigma 1 and up to approximately sigma 2 on the stress-strain curve shown, it would behave linearly. We'll get back to the behavior occurring after sigma 2 in a minute, but it's important to highlight another important mechanical material property, the elastic or Young's modulus. For any stress-strain curve, the slope of the linear portion is this modulus. In order to extract this modulus from a stress-strain curve, one merely has to take 2 points from a part of the curve which is definitely exhibiting linear stress-strain behavior and calculate the slope. This modulus is akin to the spring constant in Hooke's law. Another important feature about this elastic behavior is that it's recoverable. If one were to load up a component from 0 stress and strain to sigma 2 and epsilon 2, and then let go, the component will return to 0 stress and strain. That is to say, the deformation is recoverable. Now, if one were to load above the point roughly indicated by sigma 2 previously shown, then the deformation is no longer linear. The point of departure from linearity is shown here by the black dot. Still increasing the load, there will be a nonlinear relationship between stress and strain. This nonlinear behavior is called plasticity. What is important to appreciate here is that plastic strain, that is, strain which is imposed beyond the linear part of the curve, is not recoverable. Following a loading cycle through the linear region, into plastic and then releasing the load, there is permanent plastic strain which has been accumulated in the component, while the elastic portion of strain has been recovered. While strains in the other directions cannot be asserted with Poisson's ratio during this nonlinear plastic deformation, conservation of volume can often be employed to relate dilational quantities to others. So that's it for part 1. We have covered key concepts which allow us to appreciate the key material properties of Poisson's ratio and Young's modulus, as well as describe the conditions required to apply them during linear elastic loading of materials. In part 2, key properties which are captured during the inelastic or plastic loading will be addressed. Until next time.